Hi there. Thanks for joining us on this episode of Space Nuts. I'm your host, Andrew Dunkley. Glad you could join us once again. Coming up on this particular episode, we'll be looking at Australia's first female astronaut announced this week. Her name is Bennell Pegg. We'll tell you a little bit about her. She had to go through quite a process to get there, but it's all good news. We'll also be inspecting things within our solar system, a lava lake on Io. We'll be looking at Jupiter's water, or lack of, as the case may be, and a new theory as to why methane is being found on Mars, and it's a strange theory indeed. We'll tell you all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to take a dip in the lakes of Io is Professor Fred Watson, astronomer at large. Hello, Fred.
Yeah, you'd want to have your steel-tip boots on, I think, if you did that. But yes, it's very good to be here, Andrew. I'm delighted to be back on Space Nuts once again.
I'm glad to have you. Otherwise, I'd be sitting here making a complete fool of myself, which happens anyway. But
rather than me making a complete fool of myself, which is also what happens anyway.
That's what it's all about.
Yes, it is. Yeah.
Otherwise, we'd have to call it space normals.
Yeah,
properly.
Exactly. Yes, we will.
Yeah. And it doesn't have a ring to it at all. Now, we might as well get stuck straight in, and first cab off the rank is this announcement that we have now an Australian female astronaut, first one ever. We've had a couple of blokes, but this is our first female astronaut, and she had to really work hard to get there.
She did, yes. She so the blokes, just to get that out of the way, Paul Scully-Power and Andrew Andy Thomas, both of whom I actually have had quite a lot to do with. In fact, Paul Scully-Power once led me completely astray after an episode of the Prime Minister's Science Prizes when I shared a cab with him. I didn't end up at my hotel going to bed, which is what I expected. We ended up in a bar. So that was interesting. But to come back to reality, I've also I actually have met Bennell Pegg, and I can't remember the occasion on which it was. It was down in Adelaide. I think it was at the Space Agency because that's where she works. Her day job is the Space Agency's, and this is the Australian Space Agency, of course. She is the Space Agency's Director of Space Technology, and there must have been an event on. I think it was Enrico Palermo, who's the head of the Space Agency, who introduced me to Catherine, but I can't remember what the event was. I do make fairly regular trips down to Adelaide, where the Space Agency has its headquarters. Anyway, enough of that. What is she? She's now a fully trained astronaut. She's just finished a formal astronaut training in Germany. She is basically somebody who's always wanted to be an astronaut. Let me quote what she says in the news release. "When I dreamed of becoming an astronaut as a child, I never thought it possible to do so. Representing Australia, it's an honour to be graduating as an astronaut with the Australian flag on my shoulder." And actually, the reason why she's saying that is that I think both Andy Thomas and Paul Scully-Power have the US flag on their shoulder, because I think they were, whilst they were Australian citizens, or born Australian, I think they had US citizenship as well. So Catherine doesn't. She's actually got UK citizenship as well, a bit like me. And that means she will represent Australia. She goes on to say, "Representing Australia is filled with opportunities to propel our nation's science and technology forward in the global space arena and to raise the level of aspiration for the next generation. I hope my training and whatever comes next unlocks the path for more Australians to become involved in human spaceflight." So she's now fully qualified. It remains to be seen as to when she will get a flight. I hope she will, and I hope we'll talk about it on Space Nuts. We might even be able to interview her one day. How would that
Wouldn't that be lovely? Yes.
Yeah.
Yes. I believe she's one of 6 graduates out of an original pool of 22,500.
Yeah. There you go.
That's incredible.
It's pretty tight. Back in the 70s, there was an invitation for US citizens to apply for astronaut training. And I looked at the advert, but I didn't qualify because I'm too tall.
Really?
Yeah, 5'11" was the limit. I'm 6'4", so no chance.
Guess how tall I am, Fred?
5'11".
5'11". Yeah,
You could go. It's not too late, Andrew.
Oh, I think it probably is. Probably is. Although, if I took a leaf out of John Glenn's book, I could probably get up there. And
yeah, well, that's
much
right.
younger than when he last went.
Yes. I'm a bit young boy.
Yeah, it's anticipated that all 6 of these graduates should get into space before 2030. That's the plan, I think.
Great, it's excellent. So, yeah, we've got to keep going until 2030 so we can talk to Catherine. There's a nice comment by the person I've just mentioned, Enrico Palermo, the head of the Australian Space Agency. He says, "We're proud of Catherine. She will return to Australia a qualified astronaut brimming with knowledge, insights and connections that will help generate global opportunities for our industry." And that's good news.
It is. And to wrap it up, she's 39 and a mother of 2. That's good too. I mean, mums in space would be rare, wouldn't they?
I don't know the statistics on that, but it's something we could look at, yes. Yeah. I'll write that down. Mums in space, I like that.
How many mums in space? That's a good idea. And yes, well done and congratulations. We wish her well, Catherine Bennell Pegg. Now, Fred, let's move on to Juno. Juno, which is just a little bit further out than the moon and other places where astronauts are headed soon. But this is part of the... Sorry, we're going to Io, but Juno is the mission. Io is the closest moon to Jupiter, and they've been taking a very close look at it, and they're making some amazing discoveries on this mission.
Absolutely. So Juno, I can't remember when Juno went into orbit around Jupiter. It's been quite a while. I reckon it's been 4 or 5 years.
Possibly.
And we've had extraordinary images of the the cloud tops on Jupiter, stuff that we never really imagined because there's so much going on, as we'll talk about in a minute. There's so much going on around Jupiter's poles that you never actually see from ground-based observations. Even the Hubble telescope or the James Webb telescope, which has taken some very fine images of Jupiter, it doesn't see that structure around the North Pole, and South Poles of Jupiter. But also, what has happened is within the last, the last 6 months, back in December and again in February, Juno made close flybys of Io, the innermost of the moons that were discovered by Galileo, what we call the Galilean moons. In fact, a minimum distance was 1,500 kilometers from the surface of Io. And so lots of data taking, lots of image taking, and that's basically what we're talking about, because there's been some really quite striking imagery that's been produced. And one of the areas that was flown basically at a low altitude, and by that I mean 1,500 kilometers, was around what I think is the biggest of the volcanoes on Juno. And on Io. Io is riddled with volcanoes. It's the most volcanically active body in the solar system. It gets its heat for the activity from the fact that it's in a resonant orbits with some of the other Galilean moons. In fact, principally Europa and Ganymede. Those resonances basically squash and squeeze Io, along with the gravity of Jupiter itself, to warm up the center by friction. Basically, you've got this squeezing and squashing, and so that's why it's so volcanically active. And I think the most active, or the biggest of these volcanoes, is Loki, and it sits in the middle of a lava lake, which has been observed actually from the Earth's surface. I think we might have talked a few years ago about observations which were made from Earth of the lava lake. It's called Loki Patera, that showed that its surface kind of dried up from time to time and then turned over, that you got these kind of lava lake icebergs that actually turned over. And you might remember, and because you increase the amount of infrared radiation that's coming from it, which is how you know it's turned over. Do you remember that?
Yeah. Yes, I do. Yes.
Yeah.
And it's quite a big lake too, isn't it?
200 kilometers long, 127 miles. It's not a small lake. We'd call that an inland sea here, I think, nearly.
Yeah.
And it's lava. One of the observations that Juno has made is that there is a very strong specular reflection that comes off it, which means you're dealing with a very smooth surface indeed. And just to point out that there are available on the web some YouTube basically reconstructions of the imagery that make it look like a flyby, and they are very nicely done. They're artists' impressions, but they're made on the basis of the real imagery that Juno has taken. And certainly in one of them, you've got a nice reflection of the planet itself in the lava lake, which gives you an idea of just how smooth that surface is. And can we just move on as well to one of the other regions that was imaged?
Yes, this is amazing.
Isn't it astonishing? Because Io is so volcanically active, it's got mountains on it, and one of them is quite extraordinary. It's called Steeple Mountain. Once again, it's an artist's impression that we're seeing, which might mean that the elevation has been extended. But it's based on Juno imagery, and it looks like a cathedral with a medieval cathedral with a tall steeple with towers on it. So yes, that's probably a result of the tectonic activity on Io. So we've got really quite remarkable structures on the surface that I think are a bit unexpected. I don't think we found too much evidence of really sharp mountains, but they're being shown up by this flyby.
Yeah, they've named this one Steeple Mountain, haven't they? That's exactly what it looks like.
Yes, it does. Yeah, it's very reminiscent, actually, of the imagery, anyway, of Mont Saint-Michel. I don't know whether you've ever visited there when you've been sojourning in France, but it's off the coast of northern France. And it's a volcanic plug. It's offshore. It sits in the middle of the ocean, but it's got buildings all the way up. It's basically a monastery, and it's got this extraordinary cathedral on top with steeples that look a lot like Steeple Mountain here on Io. So that was the likeness that it awoke in my mind when I looked at this imagery.
Yeah, it's quite extraordinary. Io is just a bit bigger than our moon. Yeah. And it's sort of suffering the effects of a tug of war between other moons and Jupiter itself, resulting in all of this volcanic activity. A pretty volatile kind of place. And Juno started orbiting Io, or Jupiter, I should say, on the 4th of July, 2016. So it's nearly 8 years. That it's
8 years, wow. Doing that. What did I say, 4 or 5 years? I was, 8 years.
That's longer.
2016.
While we're talking about the Juno mission, it's also been looking at Jupiter itself and taking some scientific readings. And one of the things that scientists seem to be interested in is Jupiter's water. What have they found out there?
Well, I think this comes from analysis of the polar cyclones on Jupiter, which we're really only seeing close up as Juno gets closer and closer to the surface. And you might remember that Saturn has a polar hexagon, which is this hexagonal structure that comes from cyclonic activity. It sets up a wave in, it's a wave akin to the jet stream on Earth around the pole. Jupiter's got something similar with the sort of symmetry that we've seen on Saturn, only this is actually 8-sided symmetry rather than 6-sided symmetry. And it's this set of cyclones around the pole. There are 8 of them. But they also surround a central, a kind of mother cyclone, if I can put it that way, which is even more prominent. But what has been discovered is that the microwave radiation from that central cyclone right at Jupiter's North Pole, and we are talking about the northern polar region now, that central cyclone has a low level of microwave signature. It's much less strong than the other storms that are going around it. And so what's being inferred from this is that the structure underneath that cloud surface is very different from the other cyclones. And in fact, they're expecting, as we get more data from Juno, to be able to build what you might call a 3-dimensional map of these polar storms, so you can see how they stretch down into the atmosphere of Jupiter. And that comes from a quote by Juno project scientist whose name is Steve Levin. He's at NASA's Jet Propulsion Laboratory. So that's again related to how they are looking for the molecular structure of Jupiter's atmosphere. And it turns out that there isn't as much water on Jupiter as they expected to find, what we call water abundance. So it's suggesting, and this is by looking at molecules like oxygen and hydrogen, O2 and H2, and they, of course, are the constituents of water. That is suggesting that there is a deficiency of water on the planet Jupiter, which is unexpected. And so, it feeds into our understanding of how Jupiter formed. There's a quote which is on the NASA spaceflight website, which perhaps I can just read this because it's certainly puts it more cogently than I will. Juno's new results on Jovian water abundance suggest very low water abundance, an unexpected result that scientists are still trying to understand. However, these results do support scientists' theories that during the solar system's formation, water ice material was likely a driving force between heavy element enrichment, the process by which chemical elements heavier than hydrogen and helium were accreted or collected by Jupiter during its formation. And they're going to basically keep looking with Juno to try and work out what the distribution of water abundance is, comparing polar and equatorial regions. And no doubt we might talk about that down the track, Andrew.
We may well do. There's just so much going on. That mission is quite incredible. The fact that it's done, I don't know, getting close to 60, maybe more flybys of Jupiter. And it's done, and while it's doing that, they've been able to coordinate flybys of the near moons, yep. Which in engineering sense is just an extraordinary mission, and probably historically go down as one of the great feats of modern space engineering, I would imagine.
Absolutely. And remember, when this was being planned, and I think back in 2016, Space Nuts had already started. So I think we were talking about it then. Nobody knew whether it would survive Jupiter's radiation belts. That was always one of the big questions. Is it going to make it? And well, it certainly has. And it's doing a fine job, as we've been discussing.
It sure has. And if you want to chase up information about that Juno mission and the water on Jupiter and those incredible geological features on EO, it's on the NASA spaceflight.com website even. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, let's move on to Mars, a little bit closer to Earth, sort of. And they have we've discussed this a few times, and there's been all sorts of theories put up about why they've been detecting methane on Mars. One of the theories is it may still have some sort of tectonic activity below the surface, or it may have some primordial life that's leaking this stuff out, because most of the methane on Earth is created by living creatures. We know there aren't living creatures on Mars to this point in time, so they're thinking maybe there's something microbial below the surface that might be doing this. But a new theory has been put forward, and the cause might be us, humans.
Yes, well, partly us. That's right.
Partly us.
Yeah, which is
not directly, indirectly caused by us.
Yeah, some of it anyway. Because there's the puzzle, the methane puzzle, and it's one that goes back before we started sending Curiosity and Perseverance to Mars, because you can observe this in the atmosphere from Earth. You can detect that there is methane in Mars's atmosphere. So we knew about this a long time ago, and. Yes, exactly as you've said. Is it residual volcanism, or is it methanogenic microbes? Both of which are interesting ideas. But it's behaved in a very odd way. For example, there is one spacecraft which is a European Space Agency spacecraft. It's called the ExoMars Trace Gas Orbiter. It's in orbit, lower orbit around Mars. It's never detected methane. And that is bizarre, because that's why it was sent there, because we do see methane in the atmosphere of Mars. I think it probably means that you don't get any methane at high altitudes. And then we've got, Curiosity had a device known as SAM, Sample Analysis at Mars, which keeps on detecting traces of methane around the surface of the location where it is, which is Gale Crater, named after an Australian amateur astronomer in the early 20th century. So Gale Crater is a place where methane's detected on the surface, but in fact it's the only one so far, because none of the Perseverance doesn't have anything to detect Mars. Perseverance, of course, is in a different place. It's at Jezero Crater. So it doesn't have the ability to detect methane. But the story gets more complicated, because quite often methane is detected at night by Curiosity, but then it vanishes during the day. It varies with the seasons. As Mars, of course, has seasons. It's got a similar orbital inclination to the Earth, about 25 degrees, if I remember rightly. And sometimes it goes, way, way up, spikes to levels around 40 times greater than we normally see. So what's the story? Why do some... This is a question that's it's a lovely article on this on phys.org, the phys.org website. They pose the question, why do some science instruments detect methane on the red planet while others don't? And what they are coming to the conclusion, the new idea in this is, and it comes from NASA, it's something that's being basically studied for quite a while. In fact, it's scientists at the Goddard Space Flight Center, Greenbelt, Maryland, where this work is coming from. What they are suggesting is that the soil of Mars, which is kind of different from the soil on the Earth. We know that there's very fine-grained sand there, but also that you get, if there's a high level of salt concentration within that soil, it gets crusty. So you've got a crust that covers the lower levels. And they're suggesting that underneath that crust, and they're not suggesting how the methane is produced, but what they're suggesting is that the methane rises up and it is locked in by this crust of soil, making up the surface of Mars. And so they suggest that during summer, when it's a bit warmer, that weakens the crust, and you get methane seeping out. And that's why we see the seasonal variations in methane. But also that if you've got a rover, which weighs about the same as a car, know, on Earth, driving over this crust, it can break the crust as you drive over it and let the methane out. So that's why you're seeing it in Gale Crater, because this is where this crust is. The rover's driving over that. Every time it goes forward, it's going to stress the surface, maybe release puffs of methane. It's a really interesting idea. And as you say, it means that humans are intervening in this process of Martian methane more than we perhaps thought there was.
Well, it sort of brings into the arena the Occam's razor theory. The most obvious answer is probably the right one. And
yeah.
You can see the tracks that these rovers leave behind, and they do dig little holes and grooves, and it stands to reason that if you're driving over pockets of methane and you're cracking the surface, it's going to come up, and you're going to detect it if the rover's got that kind of equipment on board. So it could well be the reason, but it still doesn't answer the question as to how it got there in the first place.
That's quite right. That
remains a mystery. Right. Yes, but some of it that's escaping is seasonal and possibly interventional.
Yes, interventional. I like that. That's a good word.
Yeah, I love making up words.
Could be interventionistic.
Yes, well, that's even better. Gosh.
Yeah.
I like that. Yes.
Anyway.
It's an interesting theory, and one that could hold water.
Or methane, just in case, maybe. Yeah, I don't know how I don't know how you investigate this further, other than by putting methane detectors on other spacecraft. There is a comment from another scientist at Goddard Space Flight Center, which is methane experiments are resource intensive, so we have to be very strategic when we decide to do them. So it's only.
It sounds like they're half-hearted about it.
I'm not going to touch that one, Andrew. Yeah. Anyway, yes, it's hard to know how you pursue that to prove that that's the case. But maybe future surface spacecraft are the way to go. They might be more focused on answering these significant or these specific questions.
Yes, especially the question of where it all came from in the first place.
Exactly.
And is it still being produced somewhere down deep inside? Yeah, big questions. All right, very good. And yes, as Fred said, you can chase that story up on the phys.org website. That's PHYS. And don't forget to visit our website while you're online listening to us. You can do that by going to spacenutspodcast.com or spacenuts.io and have a look around while you're there. And you can listen to back episodes. You can subscribe to that thing that we have on there that I've forgotten the name of. I'm doing a Fred.
Yeah.
You're Fred.
Yeah.
Yes. Ridiculous, isn't it? Becoming a supporter is what I'm talking about. So you can do that on there. Check out the Space Nut shop, all that sort of stuff. Fred, that's where we're going to wrap it up for this episode, reminding people that our next episode's coming up in the not-too-distant future, a Q&A episode looking at all sorts of interesting stuff as requested by the audience. But until then, Fred, thank you very much. We'll see you soon.
Sounds great. Thank you, Andrew. Talk to you soon.
Fred Watson, astronomer at large, and thanks to Hugh in the studio. Let me just check and see how Hugh's going. Popped out for a cup of tea. So we'll just sit here and twiddle our thumbs for a while until you can come back and stop everything. No, we won't. But thanks for your company. Catch you on the next episode of Space Nuts from me, Andrew Dunkley. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.